Well, hello to all who is listening to me. It's really a pleasure to participate of Tecnicelpa International Conference and CIDC 2021. Thanks to the organizers for this kind of opportunity. This work deals with paper fiber suspensions and formation uniformity. Formation is an expected fundamental quality property for all paper grades, but it has particularly great relevance for low base weight sheets like tissue paper. Formation influences on structural parameters of tissue, which directly affect most of physical and other properties that are important for papers and use. As an example, formation uniformity is a key factor for creping consistency and enhanced smoothness uniformity. Formation is affected by many factors, but fiber suspension mechanical flocculation is critically harmful. So, to study the impact of fiber suspension characteristics on formation, this work had the objectives shown in this slide, that is, to give a brief overview on typical features of fiber suspensions employed specifically in tissue manufacturing and their potential effects on paper formation. This was done by interpreting theoretical impacts of tissue paper furnish compositions on pulp flocculation propensity. This slide shows the premises defined for the work. The corpus of the study was the common furnishes employed in the industry for tissue paper manufacturing. The stock consistency range was defined to be from 0.1% to 0.5%, because typically embraces boundary conditions for crescent formers and food-renier table tissue machines. The analysis method was defined to be by evaluation of mechanical flocculation potential by the crowding number concept and the evaluation of formation quality by the relative formation concept. The crowding number is recognized to be a good indicator of flocculation potential. The value of N defines the fiber suspension regime as shown in the table. For N less than 1, the regime is dilute and no flocculation is expected. For N greater than 1 and less than 60, the regime is semi-concentrated, where forced collision between fibers happens, and then some flocculation is expected. In concentrated regime, for N greater than 60, continuous contact between fibers usually happen, and this is the critical regime for flocculation. The relative formation concept is based on quantitative ratio between the variance of local base weight of commercial sheet of paper and the corresponding variance of random sheet produced from the same furnish, and is given by the relation shown on the screen. So the lower the relative formation index, the better the manufactured paper formation. This expression shows a significant correlation between relative formation and crowding number. That is, the bigger or the higher the crowding number, the higher the relative formation, or the worse the formation uniformity. In this slide, we see common tissue paper compositions for traditional products like toilet paper, facial tissues, paper towel, and table napkins. The table shows that different compositions that includes single fiber type or blended fiber pulps are employed to pursue specific properties for each kind of product. In order to simulate the fiber suspension features of each formulation, Some pulps normally used in tissue manufacturing were selected from literature to carry out the present study, as highlighted in the next slide. Here we can see different hardwood and softwood fiber characteristics, mainly from eucalyptus and pinus species. The table also shows features of recycled fiber represented by the inked pulp and non-wood raw materials like bagasse, wheat straw, and bamboo. The fiber morphological properties of all pulps in the table were used to characterize the different tissue furnishes in terms of crowding number and relative formation indexes. This slide shows fiber properties of blended hardwood and softwood pulps used in the present study. In the table, we can see how fiber length and coarseness varies as function of the increase of the mass fraction of softwood in the mix with hardwood. Now let's see the results of crowding number and relative formation evaluations of traditional tissue paper furnish compositions. Let's start by the flocculation propensity of wood pulps. The crowding number increases linearly with increasing fiber suspension consistency, but in more pronounced fashion for some of the pulps. In general, the crowd number values of select pulps were found to be between 1 and 60 in the interval of consistency considered from 0.1% to 0.5%. That is, in semi-diluted suspension regime where fiber collisions are forced, representing a certain risk of flocculation. In particular case, crowding number values above 60 that fits the fiber suspension concentrated regime were found. For instance, for the pulp with 100% softwood of pinus and high consistency, meaning that fiber are in continuous contact and flocculation is expected. Pulps containing softwood fibers are more prone to flocculation propensity, while in contrast, those containing hardwood fibers have less flocculation tendency, as shown either for kraft pulps and CTMP pulps. Softwood are primarily used for tissue paper structural reinforcement, since the higher aspect ratios can provide a stronger fiber network. But on the other hand, fiber collisions are likely easier to happen, resulting in great intensity of mechanical fiber entanglement. Now we see the flocculation propensity for non-wood pulps that shows a performance equivalence between the bamboo pulp and the softwood pulp. The results for pulp made from wheat straw and bagasse are closer to hardwood pulps, meaning that these non-wood pulps are less sensitive to flocculation. This can be explained by similarity between trends in fiber length and length to coarseness ratio. Here we have the results of flocculation propensity of toilet and facial tissue furnishes. It's clear the adverse effect of softwood content on the flocculation tendency. Toilet paper based on 100% hardwood has lower crowding number of about 15% than that blended furnish made of 70% hardwood and 30% softwood. The same effect is observed for facial tissues when softwood mass fraction in the furnace is increased from 30% to 50%. A quite high flocculation propensity was found for the furnace based on 100% of deep pulp. The selected deep pulp contains very long fibers compared to other pulps in same figure. If we look at the results for paper towel and napkins, we'll see similar results, but now I can emphasize the effect of pulps based 100% on long fibers, that is, on soft wood. The higher flocculation potential bears, as expected, to the towel and napkins furnishes made of 100% softwood, and both have similar behavior of the inked pulp. Furnish compositions employing CTMP have lower flocculation tendencies even when mixed with softwood, since CTMP tends to have shorter fibers and higher fiber coarseness. These results emphasize the impact of fiber morphology and stock consistency on flocculation potential of tissue paper furnish that directly influences on web formation uniformity that will be discussed in next slide. Next two slides display the results of relative formation computed for traditional tissue paper compositions, also for the range of stock consistency from 0.1% to 0.5%. As mentioned before, lower NF denotes better formation uniformity or lower grammage distribution variance. Looking at the results for toilet paper and facial tissue furnishes, we see that the lowest relative formation was found to the 100% hardwood or eucalyptus furnish, like in toilet paper. The combination of length and coarseness of eucalyptus fiber is what produces the lowest crowding number. In opposition, the highest crowding number and the highest relative formation index was found for the mixture of 50% hardwood and 50% softwood normally encountered in facial tissue production. In the results for towel and napkins, we can see a similar behavior. Furnishes containing hardwood in majority will show lower crown numbers and lower relative formation indexes. In opposite hand, furnishes containing softwood are those more prone to flocculation and formation unevenness, like tissue napkins and towel made of 100% pinus fibers. In summary, we saw different furnishes employed for tissue manufacturing and how they impact the paper formation. I want to highlight that eucalyptus fiber are very much compatible for tissue production due to better formation and improved quality properties. And that this work offers specific insights for challenging tasks of furnish composition selection to fulfill tissue formation objectives. Thanks for your attention. I hope that everyone will overcome these difficult pandemic times very well. Take care.
Hello everyone, I am here to present my work on effect of enzymatic pretreatment on starch catenization. To begin with the introduction, I will discuss about the use of native and cationic starch in paper making. Further moving to the experimental work, I will talk about the process of enzymatic pretreatment and starch catenization using two different reagents, namely Sheptec and betaine hydrochloride. Further, in the result section, I will talk about the degree of substitution and inherent viscosity of cationic starch. Finally, the application of cationic starch in paper making will be discussed. And I will sum up the presentation with a concluding remark. Native starch is one of the most common paper additive and is used as a strengthening agent, surface sizing agent and binder in paper coating. These native starch are non-ionic and due to this fact their applications are limited in paper making. The chemical modification is one of the best way to expand their use in different applications. Catenization is widely accepted method for modification of physicochemical properties of native starch. Cationic starch is used in paper industry as flocculating agent, retention and paper strengthening agent. However, modified starch have also been found suitable in surface treatment of paper for improving optical and printing properties. Cationic starch can be synthesized by substituting hydroxy group of anhydrous glucose unit of starch with positive charge functional groups. The higher the charge means higher the degree of substitution, which also desirable in some paper applications such as paper printability. Further in enzymatic pretreatment, corn native starch was pretreated using alpha amylase enzyme and heated for 5 minutes at 80 degrees centigrade. Further, the temperature was raised till 90 degrees centigrade for 15 minutes for cooking the starch. After cooking, the starch solution was cooled down and absolute ethanol was added to precipitate the cooked starch, which was vacuum filtered, dried and stored in the oven at 50 degrees centigrade. In the enzymatic cooking, the alpha amylase enzyme cleaves the 1,4-alpha D-glucopyranosyl linkase of amylose and amylopectin, which reduces the degree of polymerization of starch polymer. Further, the high temperature cooking, the starch granules structure become more open and dispersed. Further, these cooked starch along with the native starch were used in the catenization reaction. For starch catenization, we used three different methods. This scheme shows the first method in which Sheptec was used as a reagent. In presence of sodium hydroxide, the Sheptec converts it to its epoxy form, which further reacts with the starch molecule in aqueous medium. The end product cationic starch ether contains ether bond between starch molecule and trimethyl ammonium group. We performed the reaction for 3 hours, 6 hours and finally for 24 hours for studying the effect of reaction time on degree of substitution. We obtained cationic starch ether as a white product after precipitating it using ethanol. Further talking about the second method in which betaine hydrochloride was used as a reagent, and the reaction proceed in presence of DIC and DMAP in organic solvents such as DMF and DMSO. It was observed that the final product was bit yellowish in color and contained ester bond between anhydrous glucose unit and trimethyl ammonium group. The third reaction was also performed using betaine hydrochloride, but prior to the reaction with the starch, it was converted to N-chlorobutanyl chloride using thionyl chloride. The reaction proceeded in pyridine and final product was brownish in color. As reported in the table, a total 8 runs were performed covering all these three methods, where the first 6 runs are with Sheptec reagent. Run 7 and 8 represent the second and third method using betaine hydrochloride. FTIR was performed to analyze the functional group of cationic starch synthesized using etherification in run 3 and 6 and esterification run 7 and 8 compared with the native starch spectrum. All fundamental peaks of starch can be seen in all spectra. In compared to the native starch spectrum, a new prominent peak at 1458 cm inverse can be observed due to the quaternary ammonium group attached to the anhydrous glucose unit during the etherification and esterification reaction. Additionally, peak at 1700 and 1740 were observed due to the presence of ester bond in starch betainate. In this slide, the proton NMR spectra are shown for cationic starch ether and starch betainate and compared with the native starch spectrum. In addition to calculating the DS, proton NMR spectra can also be used for investigating the detailed structure of modified starch. The peak at 3.5 to 4 represent the hydrogen attached to the different carbon of anhydrous glucose unit. A singlet at 3.2 ppm due to the hydrogen of methyl group attached to quaternary ammonium group in cationic starch. Confirm the presence of cationic group attached to the anhydrous glucose unit. The DS was also calculated using these NMR spectra for each reaction. Further talking about the DS of cationic starches, this figure shows the effect of enzymatic cooking and reaction time on DS of cationic starch ether. It was observed that with the increase of reaction time from 3 to 24 hours, the DS increases from zero point 0.2 to zero point 0.3 using native starch as a raw material and zero point 0.3 to zero point 0.4 when cooked starch were used in the reaction. This increase is likely due to the formation of more porous starch granules, which facilitates the access of reagent to the hydroxyl group of starch. It was also observed that the cooking of starch enables the homogeneous dispersion of starch granules in the solvent by increasing the solubility. Further talking about the inherent viscosity of native and cooked starches, undoubtedly the inherent viscosity decreases with the enzymatic pretreatment as cooked starch showed the lower inherent viscosity compared to native starch. This decrease can be justified due to the cleavage of 1,4-alpha-D-glucopyrosyl linkage of amylose and amylopectin, which reduces the degree of polymerization. In fact, the hydrolysis of starch granules due to the high alkalinic and high temperature environment may also be one of the reasons for decreasing the degree of polymerization. The effect of reaction time on inherent viscosity was also studied while performing the reaction for 3 hours, 6 hours and 24 hours. Figure shows the decrease in inherent viscosity at 3 hours. Further, at 6 hours, viscosity increases slightly, but it further reduces while the reaction continues until 24 hours. The inherent viscosity was also measured for the starch betainates obtained from the esterification reaction in run 7 and 8. Figure shows the comparison of starch betainate with other cationic starch ethers from run 3 and 6. The product from the esterification reaction showed a lower range of viscosity. Hence, the same reaction were not performed using cooked starch as starch granules already faces so much hydrolysis during the esterification reaction. Also, lower DS around zero point 0.1 were obtained using run 7 and 8. Besides, a brown color product was also obtained in run 8, which could be due to the more severe degradation of starch granules at high temperature. Moving forward to the application part, these cationic starches were used to prepare the coating formulation, along with the general coating components such as alkyl quinine dimer and optical brightening agent. The native starch was used as a host component and calendered base paper without any surface treatment was used for coating operation. The laboratory coater was used for coating operation to achieve 1.5 to 2.5 gram per meter square dry coating weight. Finally, all coated paper were printed using inkjet printer. Further, the printing qualities were evaluated. As we can see in the graph, the gamete area increases along with the addition of cationic starch in coating formulation. For the starch betainate coatings, it was observed that the gamete area remained in the same range as native starch coating. The brown color of starch betainate in run 8 reduces the whiteness of coated papers, which significantly lowered the gamete area of surface coated papers. Unlike the starch betainates, the cationic starch ether coated paper showed a improvement in gamete area by 11% in run 3 and 6.5% in run 6, which may be due to the increase of surface positive charge of these coated papers. The high gamete area in run 3 can be understood by the high viscosity, which play a very important role in preparation of coating formulation. Comparing the CS in run 3 and CS in run 6, the gamete area increased for cationic starch obtained from native starch, whereas optical density and print through was better for cationic starch obtained from the cooked starch. The optical density and the print through followed the applied cationic substances on paper surface and improved with the increasing DS of cationic starches. However, a significant improvement in optical density and print through was reported using cationic starch in run 6. The other functional printing properties like intercolorability was also improved with the increasing DS for all coated papers. Besides, like Gameteria, ITCB was also influenced by the viscosity of starch, improved with the increasing of viscosity, and it decreases in the case of starch betainate. Finally, it can be concluded that the pre-treatment of starch using enzymatical cooking and high temperature converts the granules of native starch to more porous structure, which also accelerates the reaction efficiency of etherification of starch. While the cooked starch is favorable for increasing the degree of substitution of cationic starches, it faces the challenge due to the decreasing of inherent viscosity. In contrary to esterification, starch betainates were synthesized using esterification were low in inherent viscosity, and their brown color make them less compatible to use in applications such as paper coating for improving the printability. The DS and inherent viscosity of synthesized cationic starches have a strong impact in paper printability while using them in coating formulations. It was also found that the increase in DS improves the paper printability such as gameteria, optical density, print through and intercolorability. Also, cationic starches with high inherent viscosity shows an additional increase in these properties such as gameteria and intercolorability. In the end, I would like to acknowledge the project impactors for the funding of this work and Professor Paulo Ferreira, Professor Arthur, Professor Dina, Engineer Mendes, and Dr. Roberto for their supervision. Thank you for your attention.
Hello everybody, my name is Eduardo Espinosa. I am postdoctoral researcher in the Diabetes Research Group from the University of Córdoba here in Spain, and today I'm going to present the work entitled The Use of Different Wet Straw Lignocellulose Nanofibers in Cardboard Recycling Process. In this work, we will study the suitability of different nanofibrillation treatment and the property of the cellulose nanofibers obtained, and then its application as reinforcing agent on recycled cardboard. Nanocellulose is a cellulosic nanomaterial obtained from the cellulosic fiber of the plant cell wall, and to obtain it is necessary to produce the delamination of the cellulosic fiber by means of mechanical treatment. This unique property of nanocellulose makes it a great material to be used in nanocomposites, biomedicine, cosmetics, the agri-food industry, papermaking industry, as in this work, and electronics. This waste applicability allowed the nanocellulose to get a market of $300 million the last year. This nanocellulose comprises hundreds of varieties depending on its process, its origin, pretreatment, treatment, and the subsequent modification for the specific application. Therefore, it is necessary to establish a sterilization method that allows us to compare the different varieties in an objective and precise way. Some of the factors that influence these varieties and that we are needs to evaluate to get information are the chemical composition and morphology of the initial fiber, the size and surface area, for example, the surface phase, the specific surface area, the morphology of the fiber, the interaction with the medium, for example, the rheological properties, their mechanical properties and the reinforcing effect on polymers, and their impact on health and safety. We need to get these methods of analysis that are necessary to ensure adequate quality control of the product obtained and then ensure the reproducibility of these processes. As we have seen, there is a wide variety of possibility when it comes to produce cellulose nanofibers. For example, for the shown raw material, there are a multitude of combinations of pretreatment and treatment to produce it. At present, there are at least 7 pretreatment and 9 mechanical treatment, which indicate that for the same raw material we can obtain 63 different nanofibers that can be obtained. So it's very important for following standardized analysis and creating a quality index to distinguish between the different signposts and reflect information regarding the nanofibrillation and properties. In this case, first, it is necessary to define the quality requirement that will define the quality index and what analysis will be performed to reflect this quality requirement. Secondly, it is necessary to determine the scope of application for the cellulose nanofibers obtained. In this work, we are going to use the quality index proposed by the Smithsonian College and will try to explain it briefly. For this analysis, 8 parameters were established in order to represent all the aspects of the nanofibers. Half of the tests were performed on the suspension, which are called direct tests, and the other half were performed after the transformation of the suspension into a nanofiber that we call indirect tests. From the observation under the optical microscope, it was possible to characterize the macrometric fraction by analyzing the average particle size and the homogeneity of the sample. Therefore, the higher the nanofibrillation, the smaller the mean particle size, and in most cases, the greater the homogeneity of the suspension. The nanometric fraction was analyzed by 2 direct tests on the suspension by measuring, in one case, the nanofibrillation fraction, a kind of nanofibrillation yield of the centrifugation of the suspension, and by measuring the turbidity. The lower the turbidity, the higher the nanofibrillation in this case. The direct test was performed with information on the interaction of the nanofibrils, their surface area, their morphology, as well as information that is relevant to the direct test. In this index, to determine the transformation of this value of each variable on a scale from 0 to 10, nanocellulose were obtained from different plugin space using a so-called ultrafine index, collecting samples every 20 minutes to collect different degrees of fibrillation for each sample. A total of 20 values per property were taken to define in a proper way the correlation between the property and the fibrillation. With this correlation, lines from this property were obtained and a value between 0 and 10 was given, which will be used for extrapolation of this value when obtaining the result of this analysis. In order to study the suitability of this index for the analysis of different fibers, several tests were carried out. In this one, we see how pulp with different hemicellulose content were subjected to a mechanical fibrillation process, observing that when the energy consumption increased, the quality index increased. Due to the greater nanofibrillation, but it reached a plateau phase where the nanofibrillation reached its limit for this type of fibers. We also observed that fibers with higher hemicellulose content result in a greater increase and a higher quality index. It is due to the inhibition of coalescence of the cellulose nanofibers in aqueous medium when it's surrounded by hemicellulose, maintaining the nanometric size rated in fibrillation treatment and avoiding their agglomeration. In addition, the effect of pre-drying of the pulp and pre-mechanical refining before enzymatic hydrolysis were also studied, and analyzed concluding that these parameters also affect on the quality index values. Once the parameter of the quality index was established, different commercial nanocellulose were studied, that shown in dark color are treated by enzymatic pretreatment and the light ones by tempo oxidation or catatonization. And we observed that there are significant differences even when the different nanocellulose were obtained by a similar treatment as we saw in the first part of the graph. In addition, the repeatability of the same process by in different periods was also evaluated, obtaining a very similar quality index value between both treatments. We saw the effectiveness of this index for the quality control of the final products. The influence of the surface law on the index was also studied, and being this high influenced by the surface law, since it implies a greater fibrillation in this treatment. In the end, the objective that we search is an easy and fast quality index that allows us to evaluate all the properties of the nanocellulose. Then, it was proposed to limit the number of criteria required for the calculation of this index by means of a correlation matrix between the different parameters. Where beyond a correlation value of 0.6, it was considered that both parameters are dependent and that this dependence is high when it exceeds the 0.7 value. After this analysis, it was concluded that there are 4 parameters that are really independent of each other, thus setting the parameters to be analyzed for the calculation of this index in the nanofibrillation fraction, the turbidity of the suspension, the Young modulus, and the macrometric size, obtaining a new quality for the calculation of this simplified quality index. To observe the suitability of this simplified quality index, correlation were established between the original index and the simplified one, observing a high correlation between the values shown by both. So it can be concluded that both indexes reflect the characteristics of this nanocellulose in a similar way, and therefore it's simplified and faster to perform the simplified ones. The aim of this work is to analyze the influence of nanofibrillation treatment on its quality calculated with this index, and its application of these nanofibers in the papermaking industry, specifically in the cardboard recycling process. For this objective was straightaway used as raw material for the production of lignocellulose nanofibers by means of mechanical treatment, which consists of mechanical refining and PFA refiner and different separate treatments. For example, the twin screw extruder, high pressure homogenization, and Masuku ultrafine grinder, with addition of trying to improve the extrusion treatment by means of enzymatic hydrolysis as pretreatment in combination with the mechanical refining. This diagram shows the different technologies used in the production of cellulose nanofibers. In first place, the ultrafine grinder, the Masuko, the most innovative one, that is the twin screw extruder, and the classical high pressure homogenization. Four different types of lignocellulose nanofibers were obtained: pre-mechanical, homogenization, ultrafine grinder, and extruder, and the one extruder but with enzymatic pretreatment. Of these three lignocellulose nanofibers obtained by mechanical treatment, it is known that those obtained by homogenization are the ones that present the best result in year. However, all of them present very acceptable diameter values that were verified using AFM. It is observed that all of them present similar length, but if we observe the aspect ratio, that is the length-diameter ratio, we see how those obtained by homogenization present a higher value. This value is closely related to the reinforcing effect that nanocellulose can exert as reinforcement in material, so it is a special interest parameter. If we analyze the difference between the mechanical and enzymatic pretreatment in the extruder, we see how with enzymatic pretreatment we increase the yield, we obtain a smaller diameter, but there is a decrease in the length of the fiber due to the hydrolysis produced by this pretreatment. It is also affect the aspect ratio and consequently its reinforcing effect. The different lignocellulose nanofibers were applied as reinforcement in recycled paperboard and compared with the reinforcing effect produced by mechanical refining as conventional treatment. In general, the mechanical properties increase as the lignocellulose nanofiber content and the intensity of the mechanical refining increase compared to the baseline values of the recycled carbon. Setting a target value of 34-43 meters for the reinforcing effect, data that were obtained from the analysis of virgin cardboard at industrial level, we can see that this value is reached for 1.5% for lignocellulose nanofiber and 3,000 revolutions for mechanical refining, with the same effect on the reinforcing effect for the different treatments. If we observe the values where greater reinforcing occurs coincide with this maximum amount or intensity of refining, produce reinforcement of more than 300% for the rupture length, just module, and burst index. However, the tearing index was only increased at 30%. We can also observe that reinforcing intensity is similar for both technologies, but when comparing treatment, small difference as observed, being the homogenization the one that gives it the best result due to the high aspect ratio that we comment, followed by the ultrafine friction grinder, the Masuko, and finally the extrusion, but all of them very close values. If we look the effects of the pretreatment in the extruder, we see that there are no significant difference in the reinforcing effect. The physical properties were also analyzed, and we see how the thickness decreased when the increasing intensity of the mechanical refining of the nanofiber content, and in addition, density increased, porosity decreased, and Gartley porosity increased. This is due to the fiber bonding produced by both technologies, especially due to the interaction between the cellulose nanofiber and the filling of the voids in the paper matrix by the nanocellulose fibers. In the microscopic image, we can observe the effect that these lignocellulose nanofibers produce between the fibers to exert the reinforcing effect and the interaction that we were talking about. We can also observe that the nanofibers content or the intensity of the refining increased, the resistance to drainage increased due to the greater interaction with the medium where the nanofibers are added, and the surface area of the fiber increased during the refining. It was also studied how the reinforcing effect of the lignocellulose nanofiber and the mechanical refining affect the roughness of the paperboard in comparison with initial recycled substrate, and it was obtained by laser profilometry that both the addition of lignocellulose nanofiber and mechanical refining present papers with lower roughness than the untreated paperboard, due to, in one case, by the delamination of the fibers in the refining, and to the formation of surface layer of lignocellulose nanofiber that produce this smoothing of the paperboard. One of the main problems in the production of cellulose nanofiber is the high energy demand that this kind of process requires. We analyzed the energy consumption required to obtain the different types of lignocellulose nanofiber studied in this work, and we observed that homogenization process requires 32,000 kilobecquerels per ton, the ultrafine grinder, the Masuko 30,000 kilobiters per ton, and the extruded only 6,000 kilobiters per ton. In addition, if the fibers are subjected to enzymatic pretreatment before passing through the extruder, the energy consumption is reduced by 37%. If we assume, as we have seen, that all technologies achieve a similar reinforcing effect and compare the same energy required for each reinforcing intensity, we obtain that comparing the mechanical refining, the homogenization and milling, and the ultrafine grinder, the Masuko require 59% and 49% more energy respectively. However, using nanofibers coming from the twin screw extruded process, it consumes 233% less and 426% less energy if they are subjected to enzymatic pretreatment. So, in conclusion, the use of lignocellulose nanofiber obtained by extrusion is energetically stable compared to the mechanical refining using conventionally in the industry, which opened a new door to the implementation of this technology in the industry, reducing, for one case, the energy consumption and increasing the life cycle of the products. Thank you so much for your attention. If you have any question, just ask. Thank you.
Okay, good afternoon to everyone. So thanks to Afonso and Mohit for the presentations. First, unfortunately, Eduardo Espinosa, the third speaker, he had last-minute limitations and cannot attend to this Q&A moment. Okay, so we will go with questions to Afonso and Mohit, so we will have more time and opportunity to questions to both. I also encourage that you put questions in the chat to help me because I had technical difficulties and I'm sorry, I didn't follow your presentations. However, we have already some questions here to put you. Afonso, I will start with you. One question from the chat. Okay. Hello, good afternoon, Afonso. How are you?
Okay.
Afonso, one question they put here was talking about long fiber, softwood. Looking to the morphology of the fiber, what is the influence of the coarseness on the mechanical properties, namely strength and softness for tissue papers?
Okay, very nice question. There is presently normally a good discussion around coarseness of fiber used in tissue making. High coarseness produces normally a more rigid structure in the paper. So it is could be good for having, let's say, higher bulk and a higher open area or porosity. Could be good for better absorption, let's say. But if we talk about softness, I would say that the lower coarseness fibers, which are more flexible, would give a better structure, paper structure for softness, not only due to its flexibility, but the lower resistance to creping action, for instance. So presently, this is what is discussed around coarseness for tissue paper.
Okay, thank you, Afonso. Another question for you, based on the abstract. I read that considering the versatility required to produce the tissue products for a variety of end uses, is it, in your opinion, better to use a blend of different fibers for controlling product quality, or simply to concentrate on the economic advantage coming from use of a single fiber type that I suppose, based on what you wrote, is hardwood? Can you comment on that?
Yes, sure. This is a good point. Many manufacturers look for blends in order to modulate, let's say, the key quality properties for tissue. So this is not a unique solution, or when the only recommendation to use blends or use single fiber pulps. When the key properties of tissue like strength, softness, absorption are improved, and specifically some of them are pursued, different combinations of fiber pulps could be, let's say, considered. And this is the key point is to have, let's say, a wise selection of blends and fibers in order to get the better performance uh, of machine and better performance of quality parameters. This is
Okay.
what I
Yeah.
see.
Okay, thanks.
Okay.
Let's move now to Mohit. Hi, Mohit. From the
Hello.
chat, there is hello. From the chat, there is a question here. What is the advantage comparing to commercially available cationic starch? The advantage that you presented.
Okay, the commercial cationic starches are generally in the market is with the lower degree of substitution, and which are basically used in the wet end of the paper making, and which we are proposing it is for the printability of the paper, and we are going to use these starch on the surface of the paper while during the coating, let's say, and or let's say for the surfacing applications. In
Okay.
these, I'm sorry, uh, I can add into that also, uh, also we found that the higher degree of substitution is more favorable for the printability. So we are going for the higher degree of substitution with those reagents, namely Sheptec and betaine hydrochloride. Also, it's the Sheptec is more petro-based chemical, and mostly in the market, in the commercial cationic starch, they use these kind of chemicals for generating those cationic starches.
Mhm. And this enzymatic pretreatment can be used with other types of starch, like wheat, tapioca, or barley.
Yes, these strategies are we used with the corn starch, but it can be used with other starches also, and yes.
And the wet end starch also, Mohit?
Sorry, which?
To the wet end starch, can this treatment be applied, or it's only for the surface starch, as you mentioned before?
I I must say, if we are going for the higher degree of substitution, it should be used at the finishing end, and not the wet end, because uh, it will not give a good formation to the paper. If we are looking for the wet end, we can go for the lower degree substitution. We can
Okay.
make it by uh, like playing with the reagent and starch ratio. So we can make the low degree of substitution, and we can use the to the wet end, definitely.
Okay. Okay, before we move to a question that appear here to Mohit, let's put. I have another question to Afonso from the abstract that I mentioned before, Afonso. Have you already tried as a trial your strategy in a pilot or commercial tissue machine? Or and if not, do you think it is viable the scaling of the results to a pilot or at least a pilot or a tissue machine?
Yeah, I believe so. I think trials in the pilot machine would be very usual and very useful for analyzing those questions I point out in my work. The present work was not run in any pilot machine. It was a pure theoretical interpretation of mechanical population of fibers and influence formation. Because everybody knows that formation is part of quality of paper. Of course, formation uniformity is the start point of quality. And and this is like a foundation property for other key properties for tissue. And information informant trying to get better as possible, we have to look at the fiber suspension behavior and regimes. So this is a very nice opportunity for running trials in commercial or even in pilot machines.
Pilot.
Yes.
Okay, thanks, Afonso. Mohit, one more question from the chat. What was the effect of enzymatic hydrolysis on the starch structure, and what could be done eventually to generate better materials for your specific application?
Uh, the enzymatic hydrolysis is like the pre-treatment method to cleave the not the all the bonds in the starch structure, but it's like selectively like little hydrolysis. It cleaves the 1,4 alpha D glucopyrosyl linkage in the amylose and amylose pectin structure, and it yeah this I'm not sure, but we presented in this meeting like we can increase the degree of substitution, and we can make it the high degree of substituted cationic starch, which can be used in the printability applications. And uh, yeah, these cationic starch also, if you want to use any specific application, we can use in flocculation also, and the wastewater treatment if we go for other applications.
Okay. And you mentioned the results of printing quality. What were the factors that were identified as the most relevant for the quality improvement in terms of the printing quality?
Yes, if I say the degree of substitution is the most affected, most prominent uh, feature of the cationic structures for improving the gamete area. Let's say for the optical density also, the degree of substitution is more important, and the viscosity, I must say, like it should be there, because if we reduce the viscosity a lot, then the formation of the coating formulation, and we cannot rely on the uniformity of the paper while applying on the surface. So it's better to go for the high degree of substitution, and go for the little higher side of viscosity. Like we presented in this meeting with the starch betainate, we obtained some little low degree of viscosity. We are going to improve with some kind of a strategy we are having, and let's say if we can improve, and it will be improve the printability also of the papers.
Okay, thanks, Mohit. Afonso, one more question. Have you evaluated fibers treated with enzymes? Any difference between them in terms of flocculation or formation?
Okay, I have not tried that so far, but I can expect differences because all the process or chemicals or other events that interfere in fiber interrelation between fibers or fibers interconnections, this as will certainly produce different behaviors in flocking process. So I didn't check so far, but I
Okay.
expect differences. Yes,
So it's a proposal for future
could be
work.
more flocking
It
or
could be, yeah,
depending on chemicals or the enzymes, we can expect
yeah,
maybe a huge population.
exactly. Mohit, one more question from the chat. How the enzymatic hydrolysis compares with the conventional acid hydrolysis?
As I said earlier, like this acid hydrolysis is like way more severe. If we go for the acid hydrolysis or alkalinic, these treatments are a little severe for the starch structure. They go for the lower degree of polymerization, lower viscosity, and then it will be the problematic for the preparation of the coating formulation. So we just want to selectively cleave some bonds so we can improve the reactivity of the starch. We are not going to destroy the starch. So acid hydrolysis is it's not good for this kind of feature, like you can say.
Okay. Oh, wait, one more question from the chat that I had more or less the same in here in my notes. Is this enzyme treatment is more applied to coating or single surface sizing with starch?
Like it's more, I do not get the question, like it's for the coating or surface sizing, like it uh, can you repeat the question, please?
Yeah, if the treatment you think is more applicable or can be more applied in coating or in a paper single surface sizing, which I suppose you need to decrease the degree of substitution to use it in this in surface sizing.
Yeah, surface sizing, if we are talking uh, yes, the cationic structure, these kind of degree of substitution is more towards the coating applications. Uh, but if we want to apply on in the surface sizing, we can use with the native starch, not fully substituting the native starch in the surface sizing. Just substitute a portion of native starch with the cationic starch with the high degree of substitution, and the viscosity, we play with the viscosity, and you can achieve the higher the hydrophobicity of the paper with the advantage of higher printability.
Okay. So we are on time, but last question for a short answer for Mohit. Do you think to implement this in a real process in a paper mill, what will, in your opinion, will be more critical for the success of implementing this project? These technical aspects or equipment limitations?
I just need to say this thing, like if we are going for the industrial level, we just want to go for the sizing press. Like we are not going for the coating equipment wise, the coating applications, because we are working on the lower degree of like lower pickups. So these results I presented in this meeting are is towards lower pickup. So we are aiming towards the sizing press, and yes, the high degree of substitution with the which can be a great influence on the printability. And with other components, we are also in this in my project, I'm also working on other components, and these cationic starts are really useful for can be useful for higher printability. So in the future, I hope I can go till the industrial level.
Okay, in order that we don't leave any question without answer, Afonso, a last question appear. Short answer. Did you notice any dramatic change in formation due to ionic demand and demand variability?
I'm sorry, was not studied in this work.
Ah,
Uh,
okay, okay.
I have no data for that because it
No
was not
data.
tested.
Okay.
No,
Okay,
not
so we
tested.
have already, yeah, okay. Thank you both, Afonso and Mohit. We have ended, we have arrived to the end, even we have passed, I think, 2 minutes. So thank you everyone to assist, and we will see you tomorrow is the end of the work for today for the meeting. Okay? Thank you both very much for
Okay.
your nice
Thank
presentation
you.
and comments.
Thank you.
Okay? Thank you very
Thank you
much.
so much.
Bye.
Bye bye. Bye bye.
Well, take care.
Bye.